All right, hello Algebra 2 students. I appreciate you finding time to do your notes. I am recording this one well in advance. I anticipate that these may be the notes for Friday, November 8th, or possibly Monday, November 11th. So if you are taking notes in advance, keep in mind that I am not real sure when these will be, but let's have a look at them anyway. Our objective for today will be the student will learn to classify systems of equations based upon the type and number of solutions encountered. Again, potential dates for these might be November 8th, might be November 11th. We'll simply have to see how the week unfolds. As always, press pause anytime you need more time and hit play when you're ready to move on. Now, as the objective suggests, we are beginning to explore the possibility that systems may intersect each other more than once, or possibly not even at all. So let's have a look at the different classifications that there are based upon these possibilities. A system that generates a graph that has at least one intersection, which will mean at least one solution, is what we call a consistent system. I've thrown together some graphical examples of consistent systems. In the one on the left, we have two linear functions that intersect once. In the one on the middle, we have a linear function and a cubic function, and as you can see, they intersect 3 times. On the one on the right, we have two parabolas, one of them right side up, one of them upside down, and they intersect twice. These are all examples of consistent systems. When you are working to find the solution to systems like this, you may get more than one answer, but you definitely get at least one answer. Another possibility for categories is independent systems. An independent system is a system that generates distinctly different graphs. That is called independent. Now, all we're simply saying with an independent system is that when you graph your particular system, you end up with two equations, two graphs that can be distinguished from each other. Okay, not to say that they have to be different types of graphs. They can be two linear equations, like the one on the left. Could be a linear equation and a parabola of some kind. In the one on the middle, could be two parallel linear equations like the one on the right. The point is that in all cases, okay, we have different types or two distinctly different graphs. Now, when you're working on an independent system, the term independent does not have anything to do with the number of solutions that you end up with. It is simply whether they graph distinctly different graphs. So when you're working to find a solution for an independent system, you may or may not get an answer. Another category that we have is inconsistent. If a system does not generate an intersection anywhere, then it would be called an inconsistent system. Now, graphical examples for an inconsistent system, as you can imagine, okay, whatever the graphs are doing, they are doing it similarly, kind of like the parallel lines in the system on the left, or possibly parabolas that are shifted from each other but are carrying the same amplitude. They are expanding at the same rate but also heading in similar directions. Okay, so they may simply run alongside each other but never actually intersect. Okay, when it comes down to an inconsistent system, when you are working to find a solution, you end up encountering a false statement of some kind. And I'll show you what that means when we get to the examples. The fourth and final category that we have for our systems is the category dependent. Another situation that may exist is the possibility that two equations may produce the exact same graph twice. In other words, one graph is directly and entirely on top of the other. This type of a system is called a dependent system. Now, as you can imagine, a dependent system would be something like this. We end up with the exact same linear function from two different equations, but when it is graphed, they are piled directly on top of each other in such a way that every point that exists on one graph also exists on the other graph. When this happens, we end up with an infinite number of points in common. So we end up with an infinite number of solutions. If you encounter a dependent system, then what will happen is when you are trying to solve it, you will encounter a true statement of some kind, and we'll get a look at that when we look at some examples. Okay, you don't necessarily need to copy down the next 4 slides, but I would like you to participate mentally with me here. Classify the following graphs solutions. Okay, a couple of things to notice. First off, we have 2 distinctly different graphs. We also have graphs that do intersect each other. Okay, so what is the term that we use for having 2 distinctly different graphs? And what is the term that we have for graphs that do intersect each other? 2 intersections means 2 solutions. We are going to say that they are consistent because they do have solutions, and we are going to say that they are independent because they are 2 different graphs. Okay, let's look at another one. Classify the following graph solutions. Once again, 2 completely different graphs, and they do intersect each other. They are consistent because we do have an intersection, and they are independent because we get 2 different graphs instead of just one graph. How about this one? Do we have 2 distinctly different graphs? Yes, we do. Do the graphs intersect each other? No, they do not. Okay, so no solution, okay, because they do not have an intersection. That is going to cause this system to be inconsistent, but it will still be independent because we did end up with 2 different types of graphs. In this one, obviously, we have the same graph twice. Okay, so what category does that put it into? That is dependent this time instead of independent. And since it is the same graph, we have infinite numbers of solutions. Okay, so it is consistent. There are points to solve this graph. Sorry for all the sound effects that you may be hearing going on in the background. I've got my cat chasing her little toys all over the room, and I have a Minion text message sound that my daughter likes on my phone, and somebody is currently blowing up my text messages. Now, as you can imagine, the problems that we're going to be working are not as simple as, here, look at this system and tell us what categories it fits into. This is going to be an expansion of the skills that we have been working on with the substitution and the elimination methods. And at the end of the problem, we will then classify the results according to what our solutions turn out doing. Okay, so here we're looking at a system. We're told to solve and classify. So we have 2 equations, y equals x plus 2 and y equals negative 2x minus 1. So what we're going to do is, the first thing to check for is dependency. Is this the same graph twice? Okay, because if it is, we can greatly reduce the amount of work that we have to do by identifying that right at the front. So is it the same graph, or are these going to produce different graphs? Now, from what we know about linear equations, we can very easily see We have two different y-intercepts. We have two different slope values. So clearly, they are not the same line. So we can't really get away with any shortcut on that. We're going to have to do a little work. Okay, so we're going to solve by either method we have discussed, either by the substitution or the elimination method. Now that you know how to do both substitution and elimination, hopefully you have arrived at the conclusion that some problems are naturally set up better for substitution, while other problems are naturally set up better for elimination. So having both of those methods under our belt can make it much easier to solve a problem. Okay, so what do you think about this system? Okay, would it be easier to do substitution? In other words, is a variable already isolated? Or would it be easier to do elimination, where you have a coefficient from one and a coefficient from the other equation, where they are the same value but different signs? Clearly, substitution looks very good for this problem. We actually have y isolated in both cases, so we can actually substitute either equation into the opposite equation. Okay, so I'm going to take the first equation, y equals x plus 2. And the substitution method tells us that we should take that x plus 2 and plug it into the other equation in place of y. By doing that, we end up with a new equation that only has one variable in it, and it will now say x plus 2 equals negative 2x minus 1. Now what we should do is we should solve the equation for the variable that we have left. Obviously that's going to be x. Okay. So when we go through our steps for solving the equation, the first thing that should pop into our mind is that we have x's on both sides of the equal sign. So we're going to pick one direction to send our x's. I choose to send the negative 2x's to the left because I like to have my variables positive. So I'm going to add 2x to both sides. On the left side, obviously, that is going to give us 3x's, and it will eliminate the x's on the right. The next step we have should be to move everything else away from x, meaning since all the x's went left, then everything else goes to the right. That positive 2 plus 2, that does not need to be there. So to move it, we will do the opposite of plus 2, which is to subtract 2 from both sides. That'll take care of the 2 on the left, and negative 1 minus 2 is negative 3 on the right. Lastly, we have 3x's, but we do not want 3, we only want 1, so we will divide both sides by 3. That will obviously take care of the coefficient for x, and on the right we have negative 3 divided by positive 3. 3 divided by 3 is 1, and a negative divided by a positive is still negative. Okay, so we have an abscissa for our solution. Now what we're supposed to do is we're supposed to take this value back to the original system and plug it into the first equation that we started with. So y equals x plus 2. We now think x is negative 1, so we're going to plug that in for x. Y equals negative 1 plus 2. That is obviously positive 1. Now we have an ordinate to go with our abscissa, so we have a solution. Add negative 1, comma, positive 1. Okay. That's great that we have the solution. The problem did not ask us to find the solution, it asked us to classify. Okay, so what did we just discover? We have a solution. So what category does that put this into? Since it has a solution, that would make this system consistent. Now, did we determine if it was going to graph the same line twice, or was it going to be two different lines? Clearly, it was going to be two different lines. So what category does that put the system into for that, having two different graphs? That makes it independent. Okay, so one solution, and that had different graphs, so the system would be consistent and independent. Now I have a couple of more examples here. I'd like you to copy them down, and I'd like you to give them a try. You ought to be able to get to the solutions for this system as well as the next one, and then refer back to your notes on the 4 different categories and that should allow you to substitute or to classify the system based upon those definitions. So the first system is 2y equals 4x minus 1, and the next equation is 6y equals 12x minus 3. Work through and solve this system, and then see which categories you think it fits. The other system I'd like you to have a look at is 2y equals 4x minus 1, and 3y equals 6x plus 7. And again, solve these by any method you think is acceptable, either by substitution or elimination. It's up to you to decide which. Then classify. We will cover these two examples in class to make sure that you did get them right and you understand what the problems brought to the table. And I appreciate you taking time to tune into your notes. I will see you in class.